in this case visual cortex, then comes back down to the side. And this is because the cortex is more precise in deciphering sensory input, it also takes longer. Right? So this is a more refined yet slower pathway. So in this case, it could well be that this was a rope after all, and not a snake. Then the cortex will decode it and tell the amygdala, you can come down, it's not a snake, it's a rope. So it's a fine balance between these two pathways that decide whether it decides to take the majors in a healthy manner. A rat or a mouse in a cage and play a sound, just like showing the blue square, which in itself is neutral. It is not dangerous. The sound in itself is not fear-evoking. But now if you pair the same shock, same sound, with electrical shock to the tree a few times, suddenly that same neutral sound acquires a dangerous potential. It now becomes dangerous to the animal. Such that the next day, when you play the same sound back on its phone, the animal remembers something bad happened to me yesterday when I saw this bird sound and becomes afraid. And the fear response in this case is shown as a freezing response. The animal freezes, stops moving, shows its afraid. So now sound evokes the fear response. And this is what it looks like in our lab. There are two animals. When this white light comes on, that's when the sound comes on. So now the sound is being played. The same sound was paired with shock yesterday. And you can see now that this animal is very afraid, although it's just a sound. But it remembers that yesterday this was paired with a shock. This guy also underwent the same experience, but doesn't make much of it. So there are varying levels of these fear memories in animals. So this is a very simple, robust model of associative learning, a variation of Pavlovian conditioning. Now, over the last 2 decades, extensive research has now delineated how exactly this kind of fear memory is encoded within the amygdala, all the way from the behavior down to neurons and after molecules. We know the full basis, the neural basis of fear memory formation within the amygdala, both in rats and mice. We receive double the shock intensity, and then you compare the two groups to see what happens to the general. The design is as follows. First, the animals receive only the two tones, the safe tone, CS minus, and the dangerous tone, CS plus. Intermingled, animals that are scared, they're both neutral at that point. Then the CS plus, what will become the dangerous tone, is paired with the shock, and the CS minus is never paired with the shock. And next day, they're brought in a different context, and both tones are played. And then we measure how much does the animal freeze the safe versus dangerous tone. Simple behavior experiment. And what we have found is that when the tones were played by themselves, the harmony increases to either tone. But after the CS plus was paired with the shock, not the CS minus, the animal selectively increases its fear response to the CS plus, but not the CS minus. So the animal is doing a very good job of discriminating safe from dangerous. In this case, safe is white, dangerous is black. And we can replot this by showing both freezing on one axis, on one plot. So freezing to the CS plus, the dangerous tone on this axis, freezing to the CS minus, the safe tone on this axis. After the weak shock conditioning, the shock that is only half a milliampere, all of the increased freezing happens only in response to the dangerous CS plus tone and nothing on this axis. This is selectively freezing to the CS plus. In the same animal, if you implanted a gadget which was pretty ingenious, he had this multi-electrode drive, 4 independently movable drives, which are mechanically manipulated.